Hello and welcome to lesson 6 of our triple science structure and bonding topic. And today we are going to be looking again at the properties of nanoparticles, looking at their sizes and comparing them to some other types of particles. But before we do that, memory test of last lesson. You don't have to write this down, don't copy it out. Just think to yourself or discuss it with somebody in the room. What are the missing answers for 1 to 6? And then there's a 7 and 8 down the bottom. Pause it now. Here come the answers. How much could you remember from last lesson? Silver used for antibacterial plasters, but it doesn't lose its properties, so it can kill useful bacteria as well, even after it's been thrown away. Zinc oxide, transparent sunscreen. So transparent is an important property. It also blocks UV light, but because it's transparent, it could be applied to skin incompletely. Particulate coatings help windows to clean themselves. They get activated by UV light and water to help break down organic matter on windows. But they can also catalyze reactions inside the body, producing harmful substances potentially. How big are nanoparticles? They are 1 times 10 to the minus 9 meters. Why do they have unusual properties? They have a large surface area. Okay, now today's driving question, how small is dust? So we're going to be comparing dust to nanoparticles, and we're going to be looking at that in terms of standard form and also surface area to volume ratio. Right, so let's have a look at standard form. And here we've got the prefixes for standard form. So you can already see the word nano there next to 10 to the minus 9. Right, so 10 to the power of 0 is the same as 1. You might well have come across that in maths. And then kilo, as in kilogram, kilowatt. 10 to the power of 3 is 1,000. 10 to the power of 6 is a million, and that is given the prefix mega, capital M. Capital G for giga is 10 to the 9, 1,000 million, and then capital T for tera would be 10 to the power of 12. We're going to be concentrating on the small end of the scale. So 10 to the minus 3, 1 divided by 1,000 is milli, as in millimeters. Micrometers would be 10 to the minus 6. And then we've got nano, 10 to the minus 9, and pico, 10 to the minus 12. Now a cell is somewhere around about here, around 10 to the minus 5, 10 to the minus 4, around 100 micrometers. Yeah, so about 1 times 10 to the minus 4. And then what else am I going to put on this scale? Atoms. Well, an atom is about 1 times 10 to the minus 10. In other words, 0.1 nanometers, or around about 100 picometers. The nucleus of an atom is even smaller again. Okay, now nanoparticles we've learned about fit in here. So larger than an atom, smaller than a cell, around 1 times 10 to the minus 9 at 1 nanometer. So 1 times 10 to the minus 9 meters is also referred to as 1 nanometer. Now we are going to be moving backwards and forwards between meters and nanometers during this lesson. Just to remind you that nanoparticles have unusual properties due to their large surface area. And last lesson we looked at their new uses, and we looked at some benefits and drawbacks to each of those uses. But today we're going to compare it firstly to dust. So our driving question, how small is dust? Well, dust is a type of particle called coarse particles. There are other coarse particles. Dust is one example. And that has the scale of around about 1 times 10 to the minus 5 meters. So we say that coarse particles are between 1 times 10 to the minus 5 meters and 2.5, or down to about 2.5 times 10 to the minus 6 meters. Right, so the largest size is 1 times 10 to the minus 5, and the smallest size is 2.5 times 10 to the minus 6. Right, there are also fine particles which cause air pollution, smog, soot in the air. Right, so air pollution is caused by fine particles. And that is on a scale of around about 2.5 times 10 to the minus 6 meters down to about 1 times 10 to the minus 7 meters. So we have 3 different particles with 3 different types of sizes: nanoparticles, fine particles, and coarse particles. So let's summarize that. Now I've put this in nanometers because I think round numbers are a bit easier to memorize and remember. And we're going to practice converting that backwards and forwards between nanometers and meters. Right, so we've got nanoparticles, which are from 1 nanometer up to about 100 nanometers. And we looked at examples of that last lesson. Okay, fine particles cause air pollution between 100 nanometers and 2,500 nanometers in size. Coarse particles like dust are between 2,500 nanometers up to around 10,000 nanometers. We're going to concentrate on remembering those facts and then being able to convert them into meters. So here comes a memory test. So look at this slide, try and remember those sizes in nanometers, and we're about to test your memory. So here we go, pause the video, and so you don't have to write this down. It will be part of the writing task later. So this is about trying to fix it in your memory by repeating it to yourself. Can you think of one example of each type, and what was the sizes in nanometers? Pause it now. Okay, here come the answers. We saw a range of examples, so you could have put other examples in for nanoparticles. They are from 1 to 100 nanometers. Fine particles, air pollution, from 100 to 2,500 nanometers, and then coarse particles include dust, from 2,500 up to around 10,000 nanometers. Okay, right, let's start trying to convert between nanometers and meters. So nanometer is any particle around 1 nanometer in size, although it can go up to, if it's up to about 100 nanometers, we would still call it a nanoparticle. Right, then fine particles from 100 to 2,500, then coarse particles from 2,500 up to 10,000 nanometers. Let's convert this into meters. Right, so 1 nanometer is 1 times 10 to the minus 9. So we're going to replace this on the scale with 1 times 10 to the minus 9. 0.1 is 10 times smaller than that. Right, so 10 times smaller will be 1 times 10 to the minus 10. 10 nanometers needs to be 10 times bigger than that. So that would be 1 times 10 to the minus 8. 100 nanometers, 10 times bigger again. 1 times 10 to the minus 7. Then we're going 10 times bigger again. 1,000 nanometers is 1 times 10 to the minus 6. Then we're going 10 times bigger again. 1 times 10 to the minus 5. Okay, so every time we go up a factor of 10, from minus 9 to minus 8 to minus 7 to minus 6 to minus 5, we're timesing by 10. Okay, so that means if 1 times 10 to the minus 9 is 1 nanometer, 1 times 10 to the 8 is 10 nanometers, 100 nanometers, 1,000 nanometers, 10,000 nanometers. Okay, so if we got 1 nanometer to 100 nanometers, that is 1 times 10 to the minus 9, going up to 100 times bigger, minus 8, minus 7. So nanoparticles go up to 1 times 10 to the minus 7 meters. Fine particles start at that point, and then we're going 1,000. So we're going up another times 10. So we're going to minus 6, but it's 2.5 times 10 to the minus 6. Then we're starting there and going up to 10,000 nanometers. So how many times bigger have we gone compared to a nanometer? 10,000. So we've gone times by 10, 100, 1,000, 10,000. So we've gone from minus 9 up to 1 times 10 to the minus 5. Okay, so we've gone up by a factor of 10 4 times to get up to 10,000 nanometers. How confident you feel with that will depend on how good you are with going up and down in factors of 10 in standard form. Okay, oh, I've put the symbols in here. So if you're not familiar with the symbols for the standard form prefixes, it is something you will need to know for biology, chemistry, and physics. It comes up in all 3 subjects. So nano has the symbol small n, nm. If you see a small p, pico, so pm would be picometers. Micro has this Greek letter here, the Greek letter mu. So that symbol mu, followed by an m for meters, would be micrometers, 10 to the minus 6. Right, here's some practice. Now, I want everybody to do 1 to 8. If you feel really confident with this, with your maths and your standard form, you could try the extension ones as well. Okay, so these are in meters. Try and work out how many nanometers each one is, remembering that 1 nanometer is 1 times 10 to the minus 9. So think to yourself, is it going up by 10? Is it going up by 100, which would be going up by 10 2 times? How many nanometers are each of these? Pause the video, go for it. Okay, I'm going to put the answer slide up so you can work your way through it. Just before I do that, 1 times 10 to the minus 8, it's gone up by 10, so that would be 10 nanometers. Okay, right, if we're then going up by 10 to the minus 6 has gone up by 10, minus 8, minus 7, minus 6. It's gone up by 10 3 times. So it's times by 1,000. So that'd be 1,000 nanometers. Okay. If you were stuck, hopefully, you could pause it now and see if you can do a few more. Here come the answers. Well, have a look through, see if you managed to get it right. We are going to do more on factor of 10 because we're going to start looking at surface area to volume ratio. And this helps us to explain why nanoparticles have such unusual properties, even compared to coarse particles and fine particles. Just to point out, hopefully you'll have come across this in biology. If not, you will do it at some point. Surface area to volume ratio, I'm going to summarize that as SA-V ratio. For nanoparticles, because they have a large surface area to volume ratio, we say SAV ratio is large. Okay, so let's have a closer look at surface area to volume ratio. Now, volume is measured in meters cubed, and surface area is measured in meters squared. Right, now, if we imagine that this cube has a side of 1 meter, so 1 meter on each side, the surface of area of one side will be 1 times 1, or 1 meter squared. Now, a cube has 6 sides, so the total surface area of the cube would be 6 times 1 meter squared, 6 meters squared. The volume would be 1 times 1 times 1, therefore 1 meter cubed. Okay, so this total surface area would be 6 meters squared, and the volume would be 1 meter cubed. Now, let's imagine instead the cube had sides of 10 meters. The surface area of one side will be 10 times 10, 100 meters squared. And if there's 6 sides in a cube, that means 600 meters squared altogether. The volume will be 10 times 10 times 10, or 1,000 meters squared. Right, now, the surface area is normally a smaller number than the volume. The total surface area of the cube, 600 meters squared, and the volume, 1,000 meters cubed. If we had 100 meters to a side, then the area of one side would be 10,000 meters squared, 6 sides would be 60,000 meters squared, and the volume would be 1 million meters cubed, or 1 times 10 to the 6 meters cubed. Right, now, let's just summarize that. So the side of the cube is increasing by a factor of 10 each time. And if we work out the surface area of one side and then the volume, we would get these results. So this is what I just said a moment ago. Right? Now, before we work out the surface area to volume ratio, we have to take into account the fact that there are 6 sides to each cube. Right? So let's times those by 6. So for this cube, if it's 1 meter on a side, its total surface area will be 6, and its volume will be 1 meter cubed. And for a cube of side 10 meters, the surface area will be 600 meters altogether, with volume still being 1,000 meters cubed. And then for a cube with a side of 100 meters, the total surface area will be 60,000 meters squared, and the volume would be 1 million meters cubed. Now, to work out surface area to volume ratio, we do surface area divided by volume. So we get 6, then 600 divided by 1,000 is 0.6, then 60,000 divided by 1 million is 0.06. And then there's a pattern here. I want to point out the pattern, which is that as the side of the cube increases by a factor of 10, the surface area to volume ratio decreases by a factor of 10. Right? And this holds true for particles as well. Right? As the side of the cube increases by a factor of 10, the surface area to volume ratio will decrease by a factor of 10. Now, the opposite is true. If the size of the cube or particle decreases by a factor of 10, so the surface area to volume ratio will increase by a factor of 10. So the smaller the particle, the larger the surface area to volume ratio, and as the size decreases by a factor of 10, the surface area to volume ratio increases by a factor of 10. Let's put that into practice. For these two particles, well, a coarse particle like dust is 1 times 10 to the minus 6 meters across, but a fine particle is 1 times 10 to the minus 7. How many times bigger is the coarse particle? Is it 10 times, 100 times, 1,000 times bigger? What will that do to the SAV ratio? Pause the video, try and work that out. Here comes the answer. The coarse particle, if it's 1 times 10 to the minus 6, that is 10 times bigger than the fine particle. If it's 10 times bigger, its SAV ratio will be 10 times smaller. Let's look at a second example. Pause the video, try and work out this one. A nanoparticle is 1 times 10 to the minus 9 across. How many times smaller is it than the fine particle? What will that do to its SAV ratio? Pause the video, try and work that out. Here come the answers. Right, if it's 1 times 10 to the minus 9, that is 100 times smaller than 1 times 10 to the minus 7. If it's 100 times smaller, its SAV ratio will be 100 times bigger. Right, memory check. You don't need to write this down. It's a quiz, it's a test, right? Just think of the answer. Number 1, example of a nanoparticle. What was its size in nanometers? Can you remember back to earlier in the video? Oh, wrong order. Number 3, example of a fine particle. What was its size in nanometers? Example of a coarse particle. What was its size in nanometers? Pause the video, see if you can remember those facts. Go for it. Okay, here come the answers. Okay, so carbon nanotube or zinc oxide or silver. We've looked at a few different examples now. And they are 1 nanometer and it goes up to about 100 nanometers. Fine particles include air pollution from 100 nanometers to 2,500 nanometers. Coarse particles include dust from 2,500 nanometers up to 10,000 nanometers. Right, and why are nanoparticles unusual? Pause the video, work out your answers at A, B, C, or D. Here comes the answer. It is A. They have a large surface area to volume ratio, a bit of a typo there, apologies for that, as they are smaller than coarse or fine particles. If they are 10 times smaller, its surface area to volume ratio will be 10 times bigger. If they are 100 times smaller, its surface area to volume ratio will be 100 times bigger. Right, time for the writing task. We need to try and remember examples and the sizes of those 3 types of particles. We need to try and remember the size of the particles in both nanometers and meters. We need to remember that when it increases by 10, the size increases by 10, surface area to volume ratio decreases by 10 and vice versa, and use that to explain why nanoparticles are so unusual. Then there's some extension here, trying to work out that if the particle 2 has a size which is 10 times bigger, what will its SAV ratio will be like? Well, it'll be 10 times smaller, so this one will be 0.1. Now, I suggest you lay this out like a table. You could summarize it in bullet points. An example for each type of particle. What was its size in nanometers? Can you convert that into meters? Then we've got this idea of when it increases by a factor of 10, what will happen to the surface area volume ratio? And using that to explain why a nanoparticle is so unusual, then the extension. Sometimes people get a bit confused by this extension. You're comparing particle 2 to particle 1. You can see what the size has changed by, how many factors of 10 has it changed by, then predict how many factors of 10 the SAV ratio would have changed by, and what you think that SAV ratio would be. Pause the video for as long as you need to have a really good go at this work. It does get really difficult when we're using factors of 10 in standard form and this idea of a ratio, but try your best. Go for it, year 10. I'm going to move this on to the answers. I hope you've had a really good go at that. It does get really difficult with the standard form aspect of this. And please do remember, you are allowed to change your answers. You're allowed to write more in. That's part of what we do when we mark the work. Okay, here we go. Trying to remember the facts of the matter for our orange level, remembering facts and key words. We looked at plenty of examples of nanoparticles, from 1 nanometer up to 100 nanometers. Okay, and in meters, that would be from 1 times 10 to the minus 9 up to 1 times 10 to the minus 7. I keep missing that off this PowerPoint for some reason. I need to add that in. Fine particles like air pollution from 100 nanometers up to 2,500 nanometers. So there's the correct answer in meters. And then dust is a coarse particle, 2,500 nanometers up to 10,000 nanometers. There's the correct answer in meters. I'm going to move this slide on. Right, when the side of a cube increases by a factor of 10, the surface area to volume ratio will decrease by a factor of 10. A nanoparticle is around 10,000 times smaller than a coarse particle. Therefore, the SUV ratio of a nanoparticle will be 10,000 times greater than dust. So dust is a pretty small particle, and yet a nanoparticle is 10,000 times smaller. That leads to a surface area to volume ratio, which is 10,000 times bigger. That's why nanoparticles are so unusual. Right, okay, now here we go. If particle 2 is 10 times bigger, its surface area to volume ratio will be 10 times smaller, so it'll be 0.1 compared to particle 1. Particle 2 in the second example is 100 times smaller, so its SUV ratio will be 100 times bigger. 0.1 times 100 gives 10. And particle 2 in the third example is 1,000 times smaller, so the SUV ratio will be 1,000 times bigger, which makes it 500. Particle 2 in this example is 100 times bigger, so this will be 100 times smaller, so 0.8 divided by 100. Here, the particle 2 is 10,000 times smaller, so the SUV ratio will be 10,000 times bigger, and exactly what happens when we compare coarse particles to nanoparticles. Okay, right. What have you been able to achieve today? Could you describe the examples and sizes, particularly in nanometers, trying to remember those key facts? Can you start to convert between nanometers and meters? Can you explain why nanoparticles are so unusual by including the pattern of how the SUV ratio changes when the side of a cube changes? So going up by a factor of 10, going down by a factor of 10. And can you then use that in a quantitative way with numbers to calculate changes in the surface area to volume ratio by going up and down in factors of 10 when you're given the size of the cube? Okay, so some really difficult work there, really challenging. So I hope that you got on okay with that. I hope this video has helped you to understand it better. And well done for your efforts. Please do remember to go back to show my homework. Click on the quiz for this lesson and complete that. That will also help to check your understanding of this, to see how much of that you are able to take in and how much of your memory you're able to retain and how much of the work you are able to understand. Well done for all your work in this year 10. Not easy, but you're doing a really good job of putting good effort into these lessons. So well done for that. See you next time. Bye-bye.